Let's first recall the result we have proved in exercise 67. If M is an R module and F a free R module with basis indexed by I, then every element of M tensor with F over R has a unique representation in the form Mi tensor EI indexed by I, where all but finitely many Mi are non-zero. In other words, this is finite sum. So this is in the case when you have a tensor product of two R modules. One is free, another is we don't know it's free or not. If we know it's free, then we know. If both are free, then we know the tensor product is again a free R module, and the basis is given by the tensor product of basis. And you know the cardinality, you know the dimension, you know the rank of the free module. But this is some less situation. It's not that nice, but at least one way it is free. Then what can we say? We cannot talk about rank, talk about basis, but still kind of we can talk about generating element, spanning element. We can still talk about linearly dependence, something like that. But this result tells us that at least you could write it using the basis of the module F, and any element could be written uniquely in the following form. And then let's come to the first part of the exercise today. This is theorem 6.7 in Keith Kunard's lecture notes. So if F is a free R module with basis I indexed by I, then this extension of scalar from R to S. So I should say that there is a ring homomorphism from R to S. S is a ring, and we could extend scalar by, so we could change or alter R module into S module by extension of scalars, right? So suppose F is an R module, and then element here, it has R module structure. So for any, to put it better, I say X tensor Y is here, and the S module structure is defined to be S acting on the first component and then tensor Y. Okay, this is very standard. Now we're talking about this S module. We claim this is again a free module. A free R module turn into a free S module with basis one tensor EI. proof. Using this exercise 67, I just record. So this in particular S is our ring, in particular is our module, right? So we can use that result on M tensor F over R. Has all its elements. Written uniquely in the form indexed by I, then some S from big S and EI, where all but finitely many SI equals 0, right? Notice the SI tensor EI is just the same as our S module, like this, and so any element of S tensor F can be written uniquely as right, and this is saying that this form S basis for this S module, right? Firstly, it's generating. Secondly, why is linear independence? Because this expression is unique. If you have non-zero coefficient, it leads to 0, this will give you a not a unique expression, right? And so the unique expression is telling you that this has linear independence. Remark 1. So you have isomorphism as S modules, the tuple is mapped. Right? Obviously, this is isomorphism, and this expression is unique. Obviously, there is bijection and it's S linear map. Okay, so secondly, as a more concrete example, you have very quickly things like this, right? C vector space. For I ideal of a ring R, you could also have our quotient I modules. So, remark, we already have this as R modules, right? That's we already proved before. R quotient I tensor Rm is isomorphic to M quotient I, something like that. Let me think, is it exactly the same thing? Yeah. Yes. I mean, take M equals R to the power N, then its quotient is just component-wise quotient by I. Okay. Third remark. So this has an S basis. 1 tensor x to the power I. Because x to the power I form R basis for Rx polynomial ring. So we have S tensor R, Rx isomorphic to Sx as S modules. So more concrete example hold like C vector space. So very general S and R ring S also work. So this is as vector space because this is FP. So let's continue. At least let's mention this without proof, I think. And we will do another proof in the next video. So second part of the exercise, let's talk about this direct sum and product commutes with tensor product. We have seen something similar, but it's not in the sense of scalar extension. It's more like tensor with another R module. Of course, this is in some sense just particular case, but not exactly, because what we know before is it's true as R module, now we claim it's true as S module, right? So let me first write it down for R modules. indexed by I, there is an S module isomorphism. S tensor over R mi I isomorphic to indexed by I S tensor over R mi. Okay. So let's say 2.1 counterexample. When we don't have this direct sum, but instead product. We have naturalized linear map. But we don't know it's isomorphism or not. In general, it's not. So counterexamples. Very just similar counterexample as before. As in our exercise, I don't remember, 67, 66. So this is not zero because we have proved that if this is frank of R, tensor over R, or this is R vector, this is a frank R vector space, this is Q vector space, and then this is not zero if M is not torsion. In particular, this is not torsion, and so this is not zero, while this is 0. You could, so why same counterexample? Yeah, it doesn't matter because we're talking about S isomorphism, but if two sides, one is 0 as R module, then another side not 0 as R module, then still this tells you two sides cannot be S isomorphism. So which means as a Z module they are not the same, but at the same time as a Q module they are also not the same here. Okay, that suffices to conclude here.